An internal combustion engine requires 4 core elements in order to run, and that is air, fuel, spark, and compression. In today's video, I'll be talking about air and fuel, and these two are summed in what we know as the air-fuel ratio, abbreviated as AFR. So what is this ratio? Now, the air-fuel ratio is defined as the mass of air divided by the mass of fuel. Now, for any engine to run smoothly, or for any fuel that is supplied to be completely burnt, it must be accompanied by a given mass of air. And this is summed in what we know as the air-fuel ratio. So what happens is, whenever a given amount of fuel is completely burnt by a given amount of air, we can say that that mixture is stoichiometric. Let me use an example of gasoline, or what we know as petrol. Its stoichiometric or air fuel ratio is 14.7 to 1. So what this means, you require 14.7 kilograms of air in order to burn 1 kg of fuel. So that is what this ratio means. It is 14.7 to 1. In other words, you require 14.7 kgs of air to burn 1 kilogram of fuel. But where do we derive this? Now, before we go ahead to establish where this comes from, let's explain what happens when this ratio goes above or below. Now, whenever the air-fuel ratio is greater than the stoichiometric, then we can say that this is lean. In other words, it will be greater than 14.7. Whenever the air-fuel ratio is less than the stoichiometric, you can say that the engine is running rich. So let's go ahead and explain how we arrive at this ratio. I know most of you love chemistry, so today we are going to remind ourselves about some bit of chemistry. So don't be intimidated. This is something not very hard. So just play along with me, and we shall be able to understand where the 14.7 is derived from. Remember, we said for any internal combustion engine to run, we require air, fuel, spark, and compression. So let's begin with air. Now, the component in air that is utilized in the combustion of fuel is oxygen. And oxygen occupies around 23% by mass of the entire mass of air. And for the fuel, I'm going to take petrol as a case study here. And petrol is usually comprised of a number of components such as paraffins, alkanes, cycloalkanes, and others. But for simplicity, I will represent petrol as C8H18. This is an alkane. So I'm going to combine it with air. So this is fuel. I'm combining it with air, which is oxygen. Now whenever we combine these two, we end up with carbon dioxide and water. So let's do some bit of balancing here. The carbons, they are 8. So we put an 8 there, so the carbons are balanced. The hydrogen, they are 18 this side. This side we have 2. So if you put a 9 there, it means the hydrogens are also balancing. Now the oxygen this side, we have 8 times 2, which is 16 plus 9, which is 25. So if you put 12.5 here, it means you have already balanced the oxygens. Now, carbon by mass is 12, and there are 8 of them. Now we are computing the mass. Remember, the air-fuel ratio is defined as the mass of air to the mass of fuel. So let's compute for the mass of the fuel and also compute the mass of air. So the atomic mass of carbon is 12, and there are 8 of them. That of hydrogen is 1, and there are 18 of them. So this is 96 plus 18, which is 114. When it comes to the oxygen, we have 12.5 times oxygen. The mass is 16, and there are 2 of them. So this is 25, 16, which is 400. But remember, this contains the entire volume of air. And in air, we have oxygen, we have nitrogen, we also have rare gases. We established that oxygen contains 23%. Around 23% of oxygen is contained in 100% of air. So I would be safe to say 23 grams of oxygen are contained in 100 grams of air. Now, how about, remember these are in grams, how about the 400 grams? Now, the 400 grams of oxygen will mean we shall have 100 divided by 23 times 400 grams of air. This will give us 1739 grams. So what we are looking for is the ratio of this mass to this mass. So the air fuel ratio will be the mass of the air to the mass of fuel. So the mass of air in this case is 1739, and the mass of fuel, remember our fuel here, is 114. When we get this ratio, it will be around 15. Now I want us to remember that we've taken a lot of assumptions when we are doing this calculation here. One of them being that we've assumed that the petrol is purely an alkane, which is not the case because it has other components such as paraffin, it has cycloalkanes, it has aromatic compounds such as benzene and the rest. So the percentage of oxygen is more than 23, like 23.14%. When you add such assumptions, this ratio will drop to about 14.7, and that's what is usually used as the ideal value or the stoichiometric value. It will always be 14.7 to 1, meaning for any engine to run at ideal condition, we need 14.7 parts of air to 1 part of fuel. So that's where this ratio is obtained. Now, because different fuels have different air-fuel ratios, it becomes a bit tricky when we are carrying out diagnosis, and that's why a new parameter was introduced, and that is lambda. So let's go ahead and look at that. Now lambda, denoted as that, is defined as the ratio of the actual air-fuel ratio to the stoichiometric ratio. So whenever lambda is equal to 1, it means that the mixture is at stoichiometric. Whenever lambda is greater than 1, you can say that the engine is running lean. And whenever lambda is less than 1, you can say that the engine is running rich.